So we'll just go into a very simple example, much less involved than the frequency response, thankfully. We'll look at the methods we've got. Now in Genesis we can support both conduction and convection solving, and in this case we'll just look at conduction. If you want to learn about convection, please contact us and we're happy to help. Again, it does involve a bit of reading first. It's something as we've done ourselves in the office. But what I want to do is just do a simple plate here, and I'm going to put 25 watts of power into a corner point in the model. I'm going to fix two other points at room temperature, or a nice balmy room temperature of 23 degrees. And I'd like to look at the temperature distribution, and actually I'd like to understand of that 25 watts, how much of it is going through the 2 points that I've fixed, so we can understand the heat sinks going on. Okay, and what we'll do next then is load up that last model. We can close this plot and we can close this. Heat transfer, and here it is. So here's our very simple model. It's a good test of my memory here, because as I've been working through these examples, I've got various tutorial notes. This one I'm having to go on memory, so we'll test how good my memory is. So first of all, if we're doing conduction analysis, we've got our standard structural material properties here, which you'll see for steel. But what we need to define for heat transfer is conductivity. So in this case, again, through a little bit of Wikipedia searching and understanding materials, I can define thermal conductivity of steel as being 0.05, and that's watts per millimeter Kelvin. So that's the unit we're working with here. It's the amount of power per distance degree that we're traveling along. So I define that there. If you do have convection, that's what the H term is for. So with that in place, the next thing I want to do is create myself a little power source element. So it's called a CHBDY element. Never before could it be more exciting. So here I want to create myself this group holder, and I'll do this little power source, and we'll just leave that as yellow, and then I can create my element. So in the element section, create a new element, define a new original element, and then by picking this group it knows what type I want to create. And down here in this corner I can create my element by just simply selecting the face of an existing structural element. Define that. If there's convection, again there's some further options, but we won't do that in this example. So that is now in the model, and you can see that they always appear as a little wireframe. So you'll see that there on screen. So now we can go and set up our boundary conditions for this solve. So we have an additional section here called heat transfer loads, and there's two steps we can do. So again, choose new and go thermal loads. And here, the first page you'll see is what's described as SPCDs. What they are is enforced values. So in this case, I'm going to pick some nodes on the top. Let me just check my nodes I want to use. Which one shall I do? That one, 4428 and 4147. So I've got these two nodes, and I'm going to fix these at 23 degrees at ambient, so I can do that. And with those fixed, I can move on to the next page of my heat transfer interface, where I can put heat fluxes. Now, heat flux is defined as power per unit area. Now I have the knowledge, and I can prove it to everybody watching, that my element is in fact 5 millimeters in each direction, so its area is 25 millimeters squared. So if I was to define a unit heat flux, that means the power I'm then applying is, is 25 watts. It's 25 times by the area, 1 times the area, 25 I should say. Now picking these is a little bit tricky in Design Studio, so I often switch to the Display tab to hide my structural elements, which then allows me to more easily pick my little power element, and I can choose Add Heat Flux, and you get a nice little wiggly line showing that I've got my heat flux of 1, which is therefore a total power of 25 watts. With that defined, there's one other step I need to do in terms of the inputs. So the convention in Genesis, if there's any enforced motion in structures or temperatures in thermal, I have to additionally SPC or constrain the nodes here. So these are my unused structural ones. So I'll create now thermal fix, and the 2 nodes that I've already picked to define the fixed temperatures, you'll see are actually still selected. So I'm able to just set those components to be constrained in this interface. And again, essentially because this interface has been created for structural analysis, there's some quirks to using it for heat transfer. And what I do here is there are no components for the thermal. There's no X, Y, or Z in this case. So I just empty the components field and then choose set components. And you'll see it does actually put the constraint on, but it understands internally that's now a thermal constraint. So I can finish that. So with the data defined, I can then create my thermal case. So if we look here, I'm going to do heat transfer. Give myself a load case. I'll do that thermal fixing. And I'll do my thermal load set. And the output I can choose is to do my temperatures as a post-processing contour. So we'll do that first of all. Now, if we want to recover the power at these nodes, currently in version 18, there's a little bit of a quirk to do this. So we actually rely on some results outputs here. So I will leave this on the screen for a moment, so anybody watching in the future can extract it. And we'll do it here. So what we have is we additionally use something called a control script in Genesis, which you can access here. And these are actually remarkably powerful features in Genesis, where you can write all sorts of output. You can get the analysis solver to be writing your Excel spreadsheets of all your report analysis results if you get into it a little bit more. Very powerful functions to save you post-processing and just generating reports directly from the solution. But in this case, we're doing this here. So we're going to be outputting this data object here, which essentially is our heat fluxes at all of the nodes. So I'll request those, and then we can do our thermal solve. It's a nice and fast one. So let's just import that result and take a look at what we've got. So there we go. Simple as is, with 25 watts of power at this particular point and fixing these at room temperature. It's telling us that that's actually going to reach a temperature of 591 degrees C, so pretty hot from that solve. So that's typically what you're looking for. Is I've got a power source and I've got fixed heat sinks, so large objects that are cooling. We can check what temperatures I'm actually going to end up getting to, so that allows you to study that and determine if things are in a happy place. Actually, I'm going to risk it now. I hadn't planned to show this, but what we can also do is you can turn that directly into a reference for a structural load case. So I can choose to do a static load case where my model is fixed, and I can choose a thermal subcase he says, no, I'm going to leave it because I'll only end up going wrong in a live demo. I will end, conscious of time, just to confirm how we can check our powers. So we put in here 25 watts, and we want to find out how much has gone into each of these two nodes. So if I start off by looking at this node, if I just go to my grids and identify them, that's 4147. A little bit of a bit of trouble to find these. It's this file here. So we've got this data, so I can search GHR, and this is all of the powers out of each of the nodes. So we're starting at nodes 1, 2, 3, 4, 5, and so on. So I want to find out the power at grid 4147. So I can do that here. So this is the line start, 4146. So that's 4146's, and this field here is the power at grid 4147. So that's 7.7 watts is being output. So if I just have the world's most crazy sheet, 7.7, and then the other node I want to evaluate is 4428. I just go a little bit further down here now, 4426, 7, and 8, and this is 17.3 as an output. 17.3. And if I just sum those, that's always reassuring. You can see that that's our output. So we've got 7.7 watts at the one location and 17.3 at the other location. So it's just trying to make some information in there. So these are watts. In terms of this, I've got a question that's popped up, which is what are these temperatures in? And actually, they're sort of unitless. It depends what your reference temperature that you've chosen to be. It's all about the delta in temperatures. So in this case, I put 23, so I'm using the convention of 23 degrees C, and therefore the temperature at that point that did reach 591 is actually 591 degrees C. If you offset to Kelvin, it's just simply a straight offset on those values. Okay,